All right, everyone. Thank you so much for coming today for our Cohort 2 Colloquium / Science Seminar. So as you know, RESESS is typically a 10-week program or 11-week program that lasts from May to early August, but we've made some adjustments so that students who have field camp or who are on the quarter system can actually participate and do the full 11 weeks. So that's why we're here today, to celebrate the work that Amy and Diana have completed in the remaining 3 weeks after all the other interns have left. So today we're going to hear from both Diana and Amy, and first is going to be Diana Rattanasith, and she is joining us as a recent graduate from the University of California, Santa Cruz. And as you may know, she's a second-year RESESS intern working with Dr. Kevin Mahan from the University of Colorado Boulder. That's her, and Cailey Condit, Kevin's PhD student. Those were her research mentors, and her writing mentor was Dr. Yuri from Mahan, and I believe he's online. So today, Diana's going to talk to us about characterization of monazite from Big Thompson Canyon, northern Colorado.
Hi everyone, as Aisha said, I'm Diana, and this summer I studied monazites from Big Thompson Canyon, northern Colorado. Okay, so the Front Range is part of the Yavapai province, and the province is thought to be a bunch of accreted island arcs that are about 1.4 billion years old. And so Big Thompson Canyon is made up of these rocks. But there's another intrusive group of rocks that are exposed there, and they're proposed to be 1.4 billion years old. And so when magma comes up and reaches the surface, it tends to melt the rocks around the surrounding rock. And so the canyon has a beautiful range of metamorphic isograds. And isograds are basically a line of constant pressure temperature conditions that are in the form of metamorphic mineral assemblages. So the samples that I studied were from the storolite zone, which is just right here where the star is. And storolites grow in low to intermediate metamorphic conditions. And since the growth boundary is known, which is this yellow line right here, when we see both fresh and retrogressed storolite minerals in our samples, it can tell us something about the path the host rock took. So we're going to be looking at storolite in my samples. So the motivation of my project is to test whether there was a separate 1.4 billion year old intrusive event in the northern Colorado Front Range, or if it was part of the 1.4 billion year old island arc, if it happened at the same time as the arcs were accreting. But the big question is, how are we going to date these rocks? And that's through monazites. Monazites are light rare earth element phosphate minerals, and they're found in a variety of rocks. They're found in sedimentary rocks, igneous, and metamorphic rocks. They're really cool because they contain compositional domains, and these domains are thought to represent different generations of monazites, and they grow in response to the geologic processes happening around the host rock. So you could have a monazite grain with a core that's a different age than the rim around it. And in this case, we're hoping the core is around 1.7 billion years old and the rim is 1.4 billion. That's what we're hoping. So what we're going to do ultimately is use uranium, thorium, total lead chemical dating to get the various ages of these monazite grains. But in order to date these grains, we want big monazite grains, and we want to date the grains that are included in specific minerals like storolite. So this is a hand sample sized monazite grain, and this is a monazite grain in thin section. And in this case, the monazite grain is included in biotite, and we know it's radioactive. It's a radioactive mineral because halos form in the mineral that it's included in, because it disturbs the crystal lattice around as it grows out. So the first thing that we did was we looked at the 3 samples and thought, are these good samples that we can date and test? Do they have fresh storolite? Do they have retrogressed? This is retrogressed storolite in each of our samples. And this guy in particular has both fresh and retrogress. So we know these are good samples. They have what we want. The second step is we've got to find these monazites. So we use the electron microprobe to obtain a cerium X-ray, a full X-ray map, which is this guy right here. And we chose to look for cerium because cerium is it's the most prominent element in monazites. So it's kind of hard to see, but these tiny white dots are proposed monazites. The next thing that we did was we obtained an aluminum X-ray map, because aluminum X-ray maps can tell us something about the overall textures of the rock. And then what I did was I overlaid these two images in Adobe, and I highlighted all of the monazite grains. So this was great. This was at the beginning of my project. I was feeling good, but then the probe died on me. And so we had to figure out a way to obtain more data. And that's when we turned to ChemScan, Qualitative Evaluation of Minerals by Scan. For one, it's a lot quicker, which is awesome. For one X-ray map of a full section, it takes about 12 hours. And for ChemScan, we got these two sections done in an hour and a half. So that was awesome. So what we did was we wanted accessory search maps. We wanted to look for monazite, of course, but other minerals like zircon and xenotime and bdelliite in case for their suitability for more geochronological or thermochronological work, just in case we wanted to use them later on. And so each pixel is 4 microns approximately. And once we chose which minerals we wanted to find, it comes out as colors on these maps, and the rest are backscatter images. And that's the gray, the different levels of gray in this section. So after I got this data, I was super excited, but I had to process it. And what I did was I applied 3 different filters. First filter, for each thin section, I went through and I highlighted all the monazite grains. And let me tell you, there are a lot. In the first section up here, there are about 250 grains. And then in MO843, there were about 200. So that was the first filter. Second one was I went in and I looked for the top 100 grains that were of good size, because we want big monazites that we can date eventually. And another thing that I looked into was what the grains were included in, if they were included in garnet or staurolite, which will then tell me something about what happened to the host rock. So the teal are the top 20 grains that we'll eventually choose from to date, use the probe to date. So as I scanned through both sections looking at the 450 plus monazite grains, I noticed that in the section that contained the fresh and retrogressed staurolite, more than 60% of the grains were greater than 16 microns, so bigger than the sky. And in the section that just contained the retrogressed staurolite, 40% of the grains were bigger than 16 microns. So this is awesome. We know that we have good-sized monazites to date. And then again, we wanted to look at what these monazites were included in. And we found that a majority of them were in the matrix, second is in the biotite, and third is in the retrogressed staurolite. But basically, we were super excited because there are monazite grains in each of the target minerals that we wanted. This is good news. This means that we have good-sized grains, and they're included in the minerals we were hoping for. So we were able to make some preliminary interpretations from the images that I was able to get before the probe died. So these are monazite grains. This is a high-resolution image of the grains, and this is a lower magnification. And what was interesting was that these monazite grains had tiny inclusions, and the inclusions were elongated in the direction of foliation plane. So that tells us something that the monazites grew either at the same time of deformation or after, which is really cool. So not even going into dating it, and we've got some pieces of the puzzle. And then the second thing we would want to do, I haven't gotten to these parts yet, is in the images, in the high resolution images, we're going to look for zoning, and we're going to look for a core and a rim, because again, we want to see if there's a difference in age to correlate them to these two metamorphic events. So eventually, this isn't actually my work. It's actually Cailey's. These are monazite grains, but they're not from Big Thompson Canyon. These are from Montana. So eventually, what we want to do is look for the zoning and decide which spots we want to zap and get a date from using the electron microprobe. So in conclusion, the metamorphic history of Big Thompson Canyon is super complex, and although I didn't have enough time, we know that these samples are super viable to test for these metamorphic events because they contain staurolite, and we can figure out from the staurolite what happened to the surrounding rocks. And this project is super interesting because the area is really complex, and although these are just a few steps into figuring out if there were two separate metamorphic events, it's still a step in the right direction. So this summer was actually a really tough summer for me, and I just wanted to thank my mentors for sticking with me. My grandma passed away, and I just wanted to thank everyone for supporting me and sticking with me through this tough time. Thank you.
All right, thanks, Diana. Does anybody have any questions?
I'm sorry. I didn't mean to tear up or anything.
Awesome talk, Diana. I thought that was great. I was wondering, so if we weren't to focus on monazite and these rocks and to look at a different accessory phase to date, what phase would you focus on?
If we weren't going to use monazite, monazite is ideal because it contains common total lead, so we don't have to distinguish between the two lead isotopes, versus we would have to know which isotopes are in zircon. Zircon is used a lot of the times to date, but the electron microprobe doesn't distinguish between the lead. So, and another plus is that the probe is at CU and we don't have to pay for isotopic dating anywhere else. So I would use zircon, but it's a little more complicated that way.
Cool, thanks.
And that was Cailey Condit, I forgot to say. And Dave Phillips has a question.
I just have two things. One is I was amused by the microprobe failure because that is so much like real-world research. You know, you've got your plan, you're going to do this great science, and all of a sudden, oh, wait, the machine's broken. Now what? So you should be applauded for being able to change course in the middle of it and switch to the Qualitium. So that was awesome. And second of all, I'm just curious, at this stage in the research, maybe it's too early, but do you have any insight as to whether you think there were, in fact, two events, or is that still you just don't have enough information yet to say?
We don't have enough information to say. Ultimately, we want dates, because dates are solid. Then we would be able to make that correlation. But I'm leaning towards that there was an overprinting event, because that's needed in order for the different generations of staurolite to have formed. Because we see an earlier generation and an older generation. So I'm leaning towards the overprinting event for sure. But, you know, we don't know yet. More work needs to be done.
Cool, thank you.
Oh, Fran has a question.
I don't know if this was allowed, but are you going to continue the work, or what are your plans?
I really do want to continue the work because it was really exciting. Monazites are so cool, and I was talking to my mentor yesterday because he's been in the field all summer. So Cailey's really been guiding me through the project, but this project really excites me, so I definitely want to continue it. And I just graduated, and I'm job hunting, so I can definitely work on this project in the process. Yeah. I just wish I had more time to work on it.
All right. Well, thank you, Diana.